Hi, in this video we are going to talk about several exponential models, comparing them, discussing which one is used in which situation. Starting with the basic exponential model. Basic is not the official name. This is why it's in parentheses, but yes, it is the basic fundamental model that everyone starts with, and often that's the only one you need. So the function we are trying to build, the model, is for amount of something. It could be population, investment, something else. Amount after t units of time. It may be t years or t days or t weeks. It's important to note, we will talk about this in a moment. P0 is initial amount. Now, T0. B is used for growth or decay factor. Sometimes in the formula, instead of B, we write 1 plus R, where R is the growth or decay rate. Couple moments here. First of all, we need to register that this is the rate per a unit of time that we are selecting. So if you're talking about, if t is in years, then it's annual rate. If t is in weeks, then it's weekly rate, and so on. So this must correspond. All right, second comment. If you have a growth situation, it's because the rate is positive. So we are adding a positive number to 1. So our b becomes greater than 1. So this is if r is positive. This is the growth situation. And if it's decay situation, then r rate becomes negative, and then growth factor becomes less than 1. We'll look at examples in a moment. Okay, so here's our example. Initial population was 1,000. It could be population of people or moose or elephants, doesn't matter. Annual growth rate 2.3. So our unit of time is years. I should take a note of this. T is in years. Okay, so please write this equation on a paper and then come back and check. Okay, we'll come back. So, no, I don't need a red for this. Okay, so P of t equals, so the initial amount is 1,000. Now, I need to convert percent to a decimal. So I'm going to move my decimal point 2 spaces, so it becomes 0.023. And then I add it to 1, so it's 1.023 raised to the power of t. Nice and easy. So what this equation says is take the initial amount, keep all of it, but every year add 2.3% by multiplying this amount by 1.0 something. Every year by 1.0 something. Okay? So now, suppose instead of growing 2.3% a year, our population decays 2.3% a year. Because it's decay, then it will be negative 0.023. So my equation will be P of t initial 1,000. Now, instead of adding 0.023, I need to subtract this from 1. So it becomes 0.977 raised to power of t. So what's happening here is that every year we only keep 97.7% of the amount. 2.3% decays, goes away. So every time you just multiply by this number, 0.97, 0.977. Every year it decreases a little bit. Okay, the next group of models, the key word for them is compounding. Compounding or incrementing exponentially more than once per time period. We are going to focus on a time period being a year, although theoretically it's possible to consider other main time periods. But usually it's used as an alternative to annual model. So in annual model, something increments or compounds once a year. The whole year passed, boom, it increased. Another year passed, boom, it increased again. This is pretty artificial, and that's why this growth rate is called nominal. It could be a factor as well, though. Nominal means it's named, but it's not really what is happening in reality. In reality, the incrementing or compounding may happen more than once. For example, banking compounding is happening once a day. But theoretically, we can write a formula what happens if increments occur every month or every week or every day or every second. N is the number of increments or number of times the amount compounds, n times per year. So let's recall the formula. Starts the same as before. The amount at the moment t, after t years in this case, is the initial amount times 1 plus. Now, instead of just adding the rate once per year, we are dividing it by number of increments, by number of compoundings. But it occurs n times a year. But then we also need to raise it to the power of t for t years. So if you just look at this part without the t, we are saying, so we increment more frequently, and this more frequently comes in two places. Here we divide the increment in n portions, but then we do it n times a year. So it should really make sense. We are not going to look at examples here. If you just follow the formula, it should make sense. Instead, we are going to the next next type of models. Conceptually, it's a pretty complicated idea. So what we discussed, and I'll repeat it briefly. If you compound more and more frequently here, instead of once a year, maybe 12, or like every year, every hour, or every minute, or every second, this amount, the total amount, gets a little bit larger, but it won't increase infinitely big. In fact, it will be reach a certain equilibrium. In fact, when n approaches to infinity, imagine that we can increment constantly, all the time, continuously, without stopping. Then this quantity will magically approach to this quantity. Just believe it. We did demonstrate it, but it's not really easy to understand and grasp and remember. So the formula that is easy to remember as PERT actually looks simpler than other models. Let's look at a couple examples. So I wrote the examples from the previous screen with the same situation. R is 2.3%. So let's look at the growth situation. Using the continuous model, we would write it like this. So initial population the same. Then E is our base. R, we need to write it as a decimal, 0.023 T. We'll make sense of it in a moment. And here, it's a decay situation. So my R is negative 2.3%. So I am going to raise E to the negative 0.023 T power. Now, take a calculator and evaluate this and this. And then come back and we will continue. Okay, so I got this. This is approximately 1.02327, and this is approximately 0.97726. What did you notice? Of course, you notice that this number is almost the same as this, and this is almost the same as this. Why? So it's good that they're almost the same. Otherwise, the models would give like really different results. Continuous model gives a good approximation of annual process of any other exponential growth or decay process. even if it's not precisely, but you can tell it's very close, right? And this number is a little bigger, and you know why? Because the more frequently we compound, more increments, the number is getting slightly higher. But overall, it's a very accurate approximation, and the reason that a continuous model is used preferably in science, it's easy to operate. You've seen it when you solve equations, and there are other reasons from higher mathematics why continuous exponential function is much easier to work with. Okay, I have just one more thing to add to this video. Okay, now we are not going to talk about a different model. It's rather like a complication to exponential models that we need to understand. So the quote you see is copied from the Common Core standards. Use properties of exponents to transform expressions for exponential functions. For example, rewrite an expression, something like this, to reveal the approximate equivalent monthly interest rate. Huh? Okay, let's make sense out of it. So the expression I'm using here is this. So that's what we are going to use. So let's focus on this word, monthly. So remember in the very first example, I emphasized that it's important when the units match that we are talking about yearly rate in T's and years, and equation gives us annual rate. Now, our equation is in years. T is in years, right? And 2.3 is the annual rate, annual percentage rate. Okay, so how can we see the monthly interest rate? So let's think about this. A yearly growth goes like this. So once a year, or like in the for the entire year, you're multiplying by 1.023. This is the yearly growth. Now, instead, they want us to see what happens every month. So every month, we are going to multiply by something. Let's call it m. So this will be my monthly growth. This is monthly growth factor. Okay, we need to look at this first. So, before we continue, you're probably confusing this already with the compounding, monthly compounding. It's not the same. So when you compound monthly, we artificially decide, okay, take the annual rate divided by 12 and increment every month and do it 12 times a year. This is compounding, the key word, compounding. This is not it. What happens here, we still have annual growth, but we want to see what would have happened every month if we kind of were able to look inside of this year. In other words, if every month we multiply by m, by m, by m, 12 times, what would that number be? That would result in exactly 1.023. Let me write this down. So m is a monthly factor, monthly growth factor. Okay, now to solve this equation for m, you probably know that you can take 12th root, or if you don't, to undo the 12th power, we need to raise to the reciprocal power, which is the same as the root. So please evaluate this number on your calculator. Okay, so you got 1.0019. So this is the factor. So this is rate. So this is the monthly rate. I don't want to use the letter R because it may play different roles. So I'll just say, right, monthly rate is, so we move decimal point 1 to 0.19%, or almost 0.2%. Okay, so we kind of understood the monthly rate, but it's not what they ask in the problem. We want to rewrite this equation. This is another important thing to understand. Let me underline this word, rewrite. So what we want to rewrite this equation without changing it, so it must be the equivalent function, equivalent expression. I cannot change it. I cannot replace 1023 with this, okay? So, but I can replace it with the equivalent expression. Okay, so look at that result that we just got. So I wrote 1.023 raised to 112th power is equal to a monthly growth factor. So if I am raising all of this to the 12th power, then I'm going to get 1.023. That's where we are going to use properties of exponent. Because powers multiply when you raise power to another power. So going back to our expression that we want to keep equivalent, so we still keep our 1000 now. We need to replace 1023 with its equivalent. So I can write it long way. First this. Oops. And then to the 12th power. And then I need to raise this to the t power, but again, because my power multiply, I can just multiply my two exponents, 12 and t. Or I can write it a little nicer, I guess. Instead of 1.023 to 112, I can write that number. So it's 1.0019 raised to 12t power. Now, let's digest this. So first of all, we used properties of exponents as this task required. To transform expression in the following way, rewrite expression. Yes, we did not change the value of it. We just manipulated with the exponents and we replaced expression, this original expression with its equivalent. Yes, really. Maybe I should put parentheses so you could see it better. This and this, the equivalent. Okay? And this, by the way. Alright? And finally, we managed to reveal the monthly interest rate because now we see it from the equation. Okay. If I were you, I would watch this part of the video several times to really understand it. Alright, good luck.